Good morning to Dr. Jaleha and my fellow friends. I am Yi Song Ting and my group members are Leong Ji Wei, Wei Kang Ji, Dong Kan Chun and Xiu Wen Qian. Today, we would like to present a report based on the serine case study. Let us move to the first part, which is name of components. There are 4 parts consist in the serine, which are needle, hub, barrier, as well as pressure. In this report, we choose pressure as our main focus part. The next is the material selection strategy. There are 4 steps to do in this strategy. The first step is translation, second is screening, followed by ranking, and the last step is documentation. Now, we start with the first step, translation. The function of the pressure was column, and the constraint that we found was support compressive block without buckling. The second constraint was diameter of the pressure was specified. In this case, our objective was minimize the cost, and the free variable was the choice of material. We use the equation above to find out the slope of the graph, which is m equal to square root of E divided by price per unit volume. After complete the step 1, we continue with step 2, screening. In this stage, we use CES software to identify the material. We set the attribute limit to E more than 1 GPa and the price is less than 10 YMR per volume. The slope of the graph was set as 2. After the screening is done, 5 of the suitable material was screened out. We did the comment and certification towards the 5 material. The first material is PE. The PE having low density, moderate cost, low Young modulus, moderate fracture toughness, translucent, and the material of PP is having the same material properties with PE. And the third one is PS. The PS is having moderate density, moderate cost, low Young modulus, low fracture toughness, and optical quality. And the next material is silicon. The silicon having high density, high cost, moderate Young modulus, low fracture toughness, opaque. And the last material was low carbon steel. Low carbon steel having high density, low cost, high Young modulus, high fracture toughness, and opaque. And the last material was low carbon steel. Low carbon steel having high density, low cost, high Young modulus, high fracture toughness, and opaque. After that, we did the ranking step. Now, we set 2 more limits to the material chart, which were the attribute limit. There were only 3 of the suitable material in the chart. And we select the 3 material to do ranking. PP got the highest score, followed by PS, and the last one is low carbon steel. The last step was documentation. PP was chosen as our best choice of material based on the previous step. PP having low density, moderate cost, low Young modulus, moderate fracture toughness, as well as translucent. Now, I pass to Wei Kang Ji for the rest of the part. Thank you.
Thank you, Yi Song Ting. And now I would like to present my part, which are process and flowchart. Process. Processing parameters. The amount of sample that a string can hold is depends on its volume. Strings scale gradations are used to measure the volume dispensed. The pressure that the strings can withstand is specified by the pressure rating. And now the machine. There are 5 of the machines that we use to process our product. First of the machine is injection molding machine. It is used for manufacturing plastic products. The second is screen printing machine. It is used to print the injections appropriate to standard level marking. And the third is sterilization plant. It is used to sterilize the instruments or device and all those products that have to be sterilized. Next, syringe packing machine. It is used for the automatic syringe mass packing. And the last is syringe assembly machine. It is used to assemble the different parts into strings. Next, equipment. There are some of the equipment that we use in our product. For example, weighing scale, water pump, air compressor, chilling plant, testing equipment, electrical fittings and socket, set of molds for parallel, set of molds for strings, body sustain cavities. And then the procedure. There are 4 steps of the procedure. The first step is the plastic part will made, and the second is the made plastic parts were assembled, and the third is the assembled part was sterilized. And the lastly is the final product was packed. And then flowchart. Here is the flowchart of our process. The raw materials is PP, and then divided to the parallel and plunger. And then parallel is go to parallel printing, and plunger is assembled with the rubber. And then both of these parts will be assembled and finishing, and then sterilizations, and then packing and dispatching. That's all from me. Thank you. And then I would like to pass to the Leon Ziwei to present his part.
Thank you, we can see. Now it's turn to material process selection strategy. First of all, we need to classify the process, which you need to do the translation of product requirement. For the function, we need to shift the plunger. For the part constraint, the material that we chosen is polypropylene and the shape is 3D and solid. Mass strength around 0.05 until 0.09 kg. Section thickness is 2 mm, while the tolerance is plus minus 0.5 mm. And the best size will be 100,000 units. For the objective is to minimize the cost. Lastly, the free variable will be choose of process and processes operating condition. Next slide is based on the left-hand side figure. Our objective is shipping, so that we need to look on shipping and plunger material is under thermoplastic, so that we can easily identify and the process is related, which have 8 types such as conventional machine, injection molding, and etc. For the right-hand side figure, we knew that plunger is under shipping and the material is under categorized polymer. So we found out polymer shipping and it is 3D and solid. Hence, there are totally 5 classes of shipping processes such as conventional machining, injection molding, convection molding, polymer casting, and resin transfer molding. All these processes can be considered as the polymer shipping process for manufacturing plunger. For the next slide, the max is set 0.05 until 0.09 kg. Based on the figure, it shows that conventional machining, injection molding, compression molding, and polymer molding will be considered due to 4 of the material being under the limit of constraint for the plunger. Other than that, resin transfer molding is over limit, which are nearly or more than 1 kg. Hence, resin transfer molding will be eliminated from this process section. For the next slide is minimum section thickness, which is 2 mm. Plunger minimum section thickness that we set is 2 mm, and based on the figure, polymer casting is shown around 8 mm above, and it will be discussed in the process section selection. Finally, it left the conventional machining, injection molding, and compression molding process needed to continue to identify the next constraint. For the next slide, last part of the screening is the tolerance. Conventional machining, injection molding, and compression molding is between 0.5 millimeters. Thus, 3 types of the process fulfill the requirement from the constraint set, which is plus minus 0.05 millimeter. Now I pass to Dong Kang Chun.
Okay, next, the step 3 is ranking the process. The economy batch is 100,000 units. Injection molding and compression molding are still under consideration because figure above show that the economy batch size of injection molding is in the range for 100,000 units for manufacturing. Next is the relative cost index per unit is calculated. The cost of the manufacturing process will help the manufacturer to determine the most cheapest process and the most effective process by using an equation. In this table, the relative cost index per unit of injection molding is cheaper than compression molding. The first is the graph of relative cost index versus batch size of injection molding, and the second graph is graph of relative cost index versus batch size of compression molding. Comparing these two graphs shows that the injection molding process has a higher tooling cost than the compression molding process at a small batch size. However, while the batch size increased to 10,000 units, the material cost of the injection molding process is lower than the compression molding process. It is clear that the injection molding is more effective for high volume production than the compression molding process. After doing the translation, screening, ranking from various processes, there is only one process suitable to manufacture plunger, which is injection molding. This is because injection molding fulfills all constraints and objectives that set the mass 0.05 to 0.09 kg, minimum section thickness 2 mm, tolerance 0.5 mm, economy batch size 100,000 units. In a nutshell, the cost of the injection molding, around 64 to 80 ringgit, is more preferred because of the higher volume of production, which is 100,000 units compared to compression molding 69.90 to 100 ringgit. Hence, the final process for manufacturing plunger is injection molding.
Thank you, Dong Kang Chun. Now I'd like to continue the next part of the presentation, which is discussion. The first, we will talk about the effects of parameters on the performance of the product. There are two main factors that are affecting the performance of the product, which are volume. The amount of the sample that the syringe can hold depends on the volume of the syringe. The higher the volume of the syringe, the larger amount of sample that the syringe can hold. Likewise, the lower the volume of the syringe, the smaller the amount of the sample that the syringe can hold. Pressure rating. The pressure that the syringe can withstand is based on its pressure rating. The higher the pressure rating, the higher the pressure that the syringe can withstand. The lower the pressure rating, the lower the pressure that the syringe can withstand. Next is the testing and quality control. Quality control is an important step to maintain and ensure the quality of the syringe is high quality. The most common defects that appears on the syringe are burn marks. Burn marks usually appears as discoloration or dark color on the edge or the surface of the product. It usually occurs due to overheating of the material or high injection speed. Next is sting mark. Sting marks are small depression formed in the mold. Sting marks occurs due to the molten plastic material cool down too slowly, which will result the outer material is pulled inwards before it has a chance to cool down completely, which cause a recession in the material. Next is short. Short is usually appears as incomplete or defects. It happens when the molten plastic material doesn't fill in the mold cavity completely before, which will result the product being incomplete after it cools and solidifies. Next is the type of defects and countermeasure. Burn marks. Burn marks can be prevented by reducing the injection speed. This is because reducing the injection speed will prevent the air bubbles getting trapped inside in the mold of the injection machine. Reducing the temperature of the mold is another way to prevent the burn marks from appearing. Sink marks. Sink marks can be prevented by increasing the pressure so that there is more time for the material to cool and shrinkage is limited. Short can be prevented by redesign the mold with a larger gate so that the resin can flow smoothly and easily. Adjusting the injection speed and pressure can also improve the flow of the resin, molten resin. Increasing the number of air vents can facilitate the escape of any trapped air inside the material. Conclusion. The purpose of this map is to make a better understanding of the material selection and the processing of the springe in order to understand the structure property processing relationship. In the analysis in selecting the appropriate material for the springe plunger, it was found that polypropylene is the most suitable material. The suitable process involving the polypropylene material to manufacture the springe plunger will be the plastic injection molding process. In order to maximize the efficiency of the process, understanding the process of the plastic injection molding will be a crucial step. Identify the defects of plastic injection molding and coming up with a countermeasure will ensure the whole process runs smoothly to save cost and time. That's all from us. Thank you.